So on a review, molecular orbital bonding, psi, wavelength overlap, when atomic orbitals with the same phase or in phase combine to form a bonding molecular orbital. So that's the s orbital. There is a cloud around the nucleus, or as a whole, as a one electron, and then so we can give it a positive, which is the direction. So when combined with another s orbital, clouds of s orbital, one electron inside, and they come together to make a sausage shape of high electron density, overlapped completely, overlap, and this is causing the bonding sigma type. So the electron probability density of a bonding molecular orbital is large in the region of space between the two nuclei, especially between the two nuclei, where the negative electrons hold the positive nuclei together. Now we come to the bonding. This is what we talk about. Psi, 1s, 1 electron. With psi, the wave function for the atomic orbital with atomic orbital to combine to make the psi molecular orbital in the bonding full overlap. And this is the wave function of the moving of the motion of the one electron, and this is the second one at the same time. They build up a combination which is high and large wavelength or wave function. So the overlapping of two hydrogen 1s atomic orbitals with the same phase sign indicated by their identical color to form a bonding molecular orbital. Okay, and then the second one is the analogous overlapping of two waves with the same phase, resulting in a constructive interference and enhanced amplitude. Molecular orbitals and antibonding psi star. So this, when the 1s and the other 1s in different directions, which we give it as a minus and a plus. So they come in different direction. They will sit, or they will not overlap, but they force to be in a one orbital of two electrons, and the shape will be distorted, and there will be a node plane in between. This node plane, it means everyone has, they are not sitting in the same plane. So here, antibonding orbitals has higher energy than a bonding orbitals. As you know, the sigma is lower in energy level, and the sigma star will be higher. The electron probability density of the region between the nuclei is small. So here, the density is small. So it contains a node, a region where psi is 0. Psi here is 0. Thus, having electron in an antibonding orbital does not help hold the nuclei together. The internuclear repulsions make them fly apart. And here, as we said, the wave function, one in a direction, the other one opposite. So they will do this, and the node in between and the wavelength will be less in density. Now, bonding in methane, CH4, we said the SS or the S is overlapped completely, psi as one positive, and there is a PX, sorry, PY. The PY, let's say they are this is the P, which are the three types of in two loops. So the loop, you can do it as, or draw it as a circle or a ball. So there's a plus minus. This is the py axis, and there is a px axis and the pz orbital over loop of the so here the p orbital has three suborbitals. Okay, sorry. And they are consist of px, py, pz, each with two segments, plus and minus. Plus and minus here means the direction. And here is the methane, as you see, tetrahedral. And the methane has, like you can see, if you see, we draw it using the loops, all the loops, the positive in the same direction, and in the middle, the minus ones, and the angle between each phase is 109.5 degree. That's the bond angle. And here, if you bring this is the carbon itself with p orbitals, px, py, pz, and here, if we introduce 4 hydrogen atoms, so the hydrogen atoms, one electron can combine or overlap with one segment, and then the combination will do the bonding, the 4 single bonding. Each bond formed between hydrogen 1s and px, hydrogen 1s with py, hydrogen 1x with pz, and you see the other one here to form the methane. Bonding in ethylene, the ethylene CH2, CH2. So we have a double bond in the middle. They are formed from 4 electrons. So you remember the carbon, if you remember the carbon, carbon 6, 1s2, 2s2, 2p2. So here we have the valence electrons, four valence electrons. Sorry, this is the smaller, should go this one. Let's make it larger. Yeah. And here as well is the superscript. Always we do the superscript of the electrons, should be the proper way of electron configuration. And here the 6 is the subscript, which is the atomic number. So 1s2, 2s2, 2p2. So we have 4. Here we have 4 valence electrons. These 4 valence electrons will combine with 4 hydrogens. Don't forget, we have 2 of these. So we have 2 carbons. So each carbon has 4 valence electrons. This is the first carbon, 4, and the second one is 4, and we have 4 hydrogens. So, okay, how they combine? So two hydrogen will combine with 2 S, let's say, and then there is here sp2 hybridization, and the sp2 they came from orbitals, okay, overlapping of s with p. So 2 electrons in p and electron of s. Okay, an electron of s. Then we have here you remember the SP, the SPZ, and the SS combination, fully overlapped, high electron density above and below the symmetry. And these combination, as you see here, forming the pi orbitals. So we have here the 4 electrons of carbon combined with another 2 hydrogens, so leaving 2 electrons. These 2 electrons from this carbon and 2 electrons for the other carbon will do double bond. The other 2 electrons forming single bonds with the 2 hydrogen, single bond with the 2 hydrogen. So here, if you see the combination of S and PZ will form SP. And SP is fully overlapped, and it's, let's say, combination will do the high electron density. And then we have the other S with the SPZ, the other one. So it's look like they are doing SP2. And here is the pi overlapping px, and these are the px of carbon with the px. The other carbon will form the double bond. And here you can see the orbitals overlapping, and this is the right side combination of the orbitals, carbon with 2 hydrogen. And here the carbon with 2 hydrogen combined, but in the middle we have double bond sigma, fully overlapped, and from the top there are pi orbitals at the top and lower. In this case, so each carbon is tetrahedral to the right side, the other carbon is tetrahedral. Covalent bond, 2 atoms must be located, orbital of one overlap an orbital of the other. Each orbital must have a single electron. This is the covalent bond. Covalent means there are valence electrons, there are single electrons to overlap to react. As we said, single electrons can form bonding, but the double electrons, they are diamagnetic, they don't form any bonding. Single electrons, they are active, they are radicals, they are forming or responsible for forming bonds. 2 atomic orbitals merge or combine to form a single bond orbital, which is occupied by both electrons with opposite spin or paired. So when combination of 2 electrons in one orbital, so the both will spin oppositely to reduce the repulsion. Both electrons are equally shared by 2 atoms, like hydrogen, fluorine, bromine, etc. This arrangement of electron and nuclei contains less energy, more stable than isolated atoms. Always when they combine together, so overall charge will be 0, so they are stable. Before F2, if the fluorine was a single atom, so it has single electrons outside, and the other fluorine has a single electron, so they are unstable. But once they combine together, fluorine with fluorine, so the formation will become molecule and stable, less or low energy. The amount of energy per mole that is given off when a bond is formed is the same amount of energy needed to break the bond, called bond dissociation energy. So here, the same amount of energy used to combine two electrons needed the same amount of energy to break down this bond. And that bond, we need energy called bond dissociation energy. For a given pair of atoms, the greater the overlap of atomic orbitals, the stronger the bond. What gives the covalent bond its strength? It is the increase in electrostatic attraction. In an isolated atom, each electron is attracted by one positive nucleus. In a molecule, each electron is attracted by two positive nuclei. Okay, so it is the concept of overlap that provides the mental bridge between the atomic orbitals, and that means the bond orbital occupies the same region in space that was occupied by both atomic orbitals, and at the same time occupy the same favorable location with respect to the second nucleus. Okay, so overlapping are very important to build the bridge. Bridge, it means the link or a bond between the two atoms. Okay, so there was a concept of maximum overlap, first stated by Linus Pauling, 1931, and was important to understand the molecular structure, the full or the maximum overlap. That's what we said, SS or SPZ, the full to form the sigma bond. And here is the SS, full overlap, to make the sausage shape of overlapping bond formation of the hydrogen molecule. Here is separated S from S orbitals, and here is the overlapping SS, and even we can call it here 1S, 1S, but here we have SS. So the SS means they are already overlapped. So let's come to the hybridization. The hybridization. Okay, so the hybridization, excitation of orbitals. How the orbitals excited. So now, hybrid orbitals, first one is sp. So consider beryllium chloride. Beryllium chloride has no unpaired electrons. Beryllium itself has no unpaired electrons, because you remember beryllium is found on its own. So there is no any single electrons, and I remember beryllium has one s2, and that's it. Beryllium. How are we to account for its combining with two chlorine atoms? The bond formation is an energy releasing. So beryllium 1s2, 2s2. So sorry. So beryllium atomic number is 4. 1s2, 2s2. If we use the, we have to write 2p because the 2p is belong to the second main shell. The main shell, the second main shell formed by or consists of two suborbitals, s and p, or two orbitals, let's say two orbitals in the second main shell. So 2s and 2p. So once we started, we have electrons 2s, we have to leave the 2p empty. And this is important for the hybridization, for moving electrons from lower energy level filled with electrons to an orbital empty orbitals. So now bond formation is energy releasing, stabilizing process. Tendency is to form bonds, and as many as possible, even if this results in bond orbitals that bear little resemblance to the atomic orbitals we have talked about. If our method of mental molecule building is to be applied here, it must be modified. So we must invent an imaginary kind of beryllium atom, one that is about to become bonded to two chlorine atoms. Okay, so now what does that mean? Means that the beryllium chloride, as we said before, we need to see single electrons to form bonds. So how come beryllium have two double bond in 1s, two electrons in 1s and two electrons in 2s? So we don't use 1s. As we said, these are the core electrons. We depend on the valence electrons. Valence electrons are the outer shell electrons. So here we have two. So how come two chlorine comes and form beryllium chloride without, okay, with two or one pair of electrons in the 2s? That's not possible. So these two electrons should be singled, should be separated. When they will be separated? When? Once, if the beryllium on its own, so they are stable with the beryllium. But when chlorine approaches the beryllium, that will excite, that will give energy to the beryllium. If we apply energy as well to break these two electrons and to break them to two singles, so in this case, we will form two single electrons with two singles of the chlorine. Okay, so here, this is mean excitation and leading to hybridization. So hybridize these two electrons to be singles. So one of them to move to the next energy level in P, and the other one will stay in 2s. Okay, let's see what will happen. So now, if you hybridize the two electrons in S, one of them will move to P, excited, go to the next energy level. So one electron promoted. So now we have two unpaired electrons. So this provides two unpaired electrons, which are needed for bonding to two chlorine atoms. We might now expect beryllium to form one bond of one kind using the p orbital and one bond of another kind using the s orbital. Okay, so this single electron will form a single bond with chlorine. This another, or the first single electrons will form another single bond with the other chlorine atom. So now we are forming two single bonds with two chlorines. Let's see, beryllium here. So one electron in S, one electron in P to the left side. Each, this is the single bond, and here is single bond. This is not minus, it's a bond. So bond angle is here, 180. So how it happened? So we have S, okay, S electron. We don't mention the two S1. We just say S electron. S electron from the beryllium bond to a chlorine, and P electron bond to another chlorine. So what do we have? We have SP hybridization. SP. Okay. So what does it mean? Means that there is a bond S. There is one electron from the beryllium, the central atom. So this SP belongs to the central atom. So one electron in S and one electron in P, they will form SP, hybridization, to bond, to make two single bond with two chlorine. Hybridization SP2. Where can we find this? In BF3, trifluoroboron. So it's fluoro. Trifluoroboron, where boron 5. So we need to know the hybridization of the central atom in this molecule, which is the boron. Boron has five electrons. 2s, 1s2, 2s2, 2p1. We don't care about 1s2. We care about the valence electron. So we have 3 electrons in the outer shell responsible for bonding. Okay, if we see this single electron, this is easy to form single bond with 1f. But what about 2s2? So these s2 electrons are doubled here. They cannot form bonding unless they are separated. So what will happen? One electron from here will promote it to the empty orbital of p. It will not come to this electron. You remember the filling the orbitals singly, then doubly. So when this electron here separated in the 2s, so it can be moved to the, not here, but in this empty orbitals. So now we left with one electron in S, one electron in P, one electron in P. So these 3 electrons being separated in three orbitals. Now they are ready for bonding. You see, as they are singles, they are ready for bonding. So now one electron promoted, 3 unpaired electrons. When they are unpaired, in this case, they are ready to form bonds with 3 fluorine. You see? So now, what do we have? We come back. We are using SPP. SPP. So when you combine the PP, they will become P2, P to the power 2. So here, bond is formed. That's belong to the hybridization, hybrid orbital sp2, belong to the central atom, boron. Not for fluorine, but for the boron. So the boron can do bonding using one electron in S, and one electron in P, one electron in P. So I can write it down here. So I can write it down that the boron is 1s2, 2s. Okay, yeah, it was 2s2, 2p1, but it will be now 2s1, 2p1, 2p1. So I'm repeating them. So, okay, this is a promoted electron. This here is the original electron in P. This one is original electron in S. So now this is how we separated the two electrons in S and we put one of them in P. So now I have 3 orbitals, as you see here. 3 orbitals, each with single electron. Each with single electron, ready to combine with F, Okay, let's leave the dot here as a 1 electron, F, 1 electron, F, 1 electron. So now they are ready to combine with them. Each fluorine will give 1 electron to the P here to form a single bond, the other fluorine with this P to form another single bond, and this F will give 1 electron or share 1 electron with this S electron to form a single bond. So now what hybridization I have? I have SPP. It means sp2. So the hybridization will be sp2. Now, this is it. SPP, it means SP to the power 2. This is the hybridization of the central atom, boron, used to form 3 orbitals singly. So here we have a triangular shape, and the separation or the bond angles for each one of them is 120 degree. This is it, a triangular or trigonal planar shape of boron fluoride, trifluoride. So it's important to memorize the bond angles for each. One of them is 120 degree, and the hybridization for BF3 is sp2. Okay, sp2. These hybrid orbitals called sp2 formed of mixing 1 electron from S and 2 electrons from P with the fluorine with the 3 orbitals fluorine. They lie, sorry for this language, lying, they are lying in a plane and directed to the corners of triangles. So each one, so this is S, P2, sp2, sp2. The geometry called trigonal or 3 corners arrangement. Trigonal. BF3 arranged in centered boron and cornered fluorine with the maximum sp2 overlap. So this is the most stable formula or structure, and they are all BF fully separated, repelled with 120 degree. That's the only way can be found, because they are very well separated in this. You know, 3 of 120 will be 360 degree. Okay, so triangles is the most stable formula or shape for BF3. Hybridization sp3, we can find it in the methane. So the carbon 1s2, 2s2, 2p2, and paired electrons in the s, in 2s, 2 unpaired electron in p. So let me write it down in 2s, 2 unpaired electrons in p, 2 unpaired electron in 2p, let's say. So 4 hydrogen atoms each has 1 unpaired electron. And you can see here, we have carbon 1s2, 2s2, 2p2. So now if in this case, the 2s as well, 1 electron will be promoted to this empty orbital to leave 4 single electrons. 1 in s, 1 in p, 1 in p, 1 in p. So I have s, p, p, p. Combined together will be sp3. So here, the hybridization, carbon on its own, being promoted 1 electron, and then the carbon once like they are in the sp3. So this was spp, it means sp3. So that's the hybridization of the carbon molecule inside methane. And that's the structure. It's tetrahedral. Tetrahedral, it means 4 faces. This is 1 face, second, behind, third, underneath, another face, and it is 4 faces or tetrahedral. So the tetrahedral faces with sp3 hybridization. And this is the shape, tetrahedral. It's carbon, hydrogen to the top, and these are the base. Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. These are at the base. Okay. So the angle between hydrogen, carbon, hydrogen will be 109.5 degree. And with the water, H2O, you can see that we have 1 oxygen, 2 hydrogens. Oxygen 1s2, 2s2, 2p4. You see 2p4. So here they are already, let's say you have only 2 electrons singly here. And for the shape, if you see, it is lone pair and lone pair. So when there's a lone pair put in the top, the other lone pair here, and 2 single electrons being used for bonding with 2 hydrogen. So the shape here is tetrahedral as well, but they are not from bonding, they are from the lone pairs. 2 bonding, single bonding, and 2 lone pairs. And even we can, it's look like tetrahedral, but in real, it's the angular geometry. Angular geometry. This is the right 105 degree. Been found using crystallographic analysis. Crystallographic analysis and been used to see the water. It is not a perfect tetrahedral. Why? Because 2 oxygen. The tetrahedral, if you come back, see the tetrahedral here is, what's that? The tetrahedral is 109.5, whereas in the water is 105. So we cannot say it's a tetrahedral. It should be angular or less, is not perfect tetrahedral. So two corners occupied by 2 hydrogen. The hybridization here is sp3. So there is 2 electrons in S, 2 electrons in P, but we have the bonding PP. P here, responsible to bond with two hydrogens as a single electrons, two single bonds. Okay, we come to the ammonia. The ammonia here is what? 1s2, 2s2, 2p3. 2p3, so I have 5 electrons in the outer shell. Okay, 5 electrons. Now, let's see what the 5 doing. So we have the 3 single electrons in the p. Okay, so I can insert a text here. And this nitrogen is 7. So 1s2, 2s2, 2p3. And here you see 2p3, 2s2. Okay, so these are 5 electrons I have. So three electrons in p, they are singles, and we have double electrons in the s. So the double electrons is not involved, they are non-bonding, they will stay as a lone pair. The other 3 electrons in p, they will form single electrons with each of the 3 hydrogens. And the best structure can be found, and the good separation, the good repulsion between the orbitals, the bonding orbitals, is what is a tetrahedral here, and the lone pair at the top, whereas the base is NH3, NH3, NH3. Sorry, NH, NH, NH. So 107 is good for the tetrahedral. Okay. And then the arrangement is okay. But tetrahedral, we can call it a trigonal pyramidal, because that trigonal pyramidal is the best if we ignore the lone pair. Lone pair here are the top. So here we have a pyramidal, and it's a trigonal, 3 phases of pyramid. So the real geometry is trigonal pyramidal geometry. Okay, we stop here. Thank you.